theory of Hecke algebras, of Wall groups, and of finite groups of Lie type. We also have several books in these areas, and we will talk about character theory of finite groups of Lie type.
Thank you very much. Right, yeah, so this is the first lecture of this week, which is an honor for me to deliver this lecture, but it's also kind of a difficult job because we have to get somehow the stage set correctly. So in these lectures, or in this first lecture particularly, I would like to introduce some basic notions about algebraic groups, which form the background for this character theory of finite groups of Lie type. So this first lecture here will be, of course, required knowledge then for my further lectures, but it will also be useful, I guess, for the lectures by Donna Testermann and Olivier Dudas, who will also speak in some sense about groups of Lie type or finite groups of Lie type. Okay, so I decided to do this with slides. I guess they will be put on the webpage immediately after the talk, so that you have this also as, say, reference material easily available. So I guess the note taker cannot get paid for this then. Well, don't imagine that I invented this first slide with these circles and colors. This is the new corporate design of my home university, and we are supposed to use that whenever they let us go out into the world. Yeah? So we have to use these circles and these colors on the first page. What we do afterwards doesn't matter. Okay, so let's see. So as I said, I hope this talk will be useful not just for those who have an immediate interest in this, but also to others. And furthermore, I hope that even the first 10 minutes may be useful to everybody participating in this program, and not just those who care very much about algebraic groups. So let's start then. Yeah, and we start, of course, with the great theorem. What is the great theorem? That's in the context of this program, I guess it's the classification of finite simple groups. So let's give a 3-slide introduction to the classification. Well, the theorem says this. So the finite simple groups are known. So either it's groups that were known anyway, or there are 26 exceptions, the 26 sporadic simple groups. And which were the groups that were known anyway? Well, it's the cyclic groups of prime order, the alternating groups AN, if n is at least 5, and the simple groups of Lie type. So I just give these two references here. This article by Aschbacher in the notices of the AMS. If you are a bit familiar with the history of this classification, it was first announced around the 1980s, and there was some issues about the proof, and in this article Aschbacher then finally announced that the proof of the classification is complete. And the other references are these series of books by Gorenstein, Lyons, and Solomon, whose aim is to write up a complete proof of the classification. Yeah. So what we will concentrate on in this talk is this class of groups, the simple groups of Lie type, or more generally finite groups of Lie type, where we will focus on the ordinary character theory on these finite groups. For example, Olivier Dudas will then also speak about modular characters of these groups. And I will not give exact references at each single step and each single theorem, but most of what I'm going to talk about is due to George Lusztig, and he wrote a very nice survey article on this whole subject, which is available there in the archive from 2014. This is actually the lecture he delivered at the occasion when he received the Shaw Prize. So this I can really recommend. It's a non-technical, gentle introduction to his work, at least the work on character theory of groups of Lie type. So in the context of the classification of finite simple groups, perhaps it's worthwhile to point out why these simple groups of Lie type play such a special role. Well, already in this formulation you see that, well, maybe you can't see it immediately, but they form somehow the largest piece of groups in this setup. And to show this graphically, I have to show this slide. I found this slide, or we found this slide 2 years ago. A periodic table of the finite simple groups. So each box stands for a finite simple group. They are arranged like atoms in some kind of order. So for example, there on the right column, you have the cyclic groups of prime orders. It's always from top to bottom. The order is increasing. On the left-hand side, you have the alternating groups. Here on the bottom, you have 26 boxes corresponding to the sporadic simple groups, and all the rest are the simple groups of Lie type. Well, it's very small, so let's have a look here. So the different colors indicate different types of groups, and also I wanted to show this is not. I did not prepare this slide. You can find, if you type in Google periodic system of simple groups, you find this page by Ivan Andrush, who put it there. He even has a blog where he explained why he had to do this. So he's not a professional mathematician, but while he was a PhD student, he wanted to find a way to explain to his father in as nice and gentle a way as possible what he's doing in his PhD. And so this is why he came up with this periodic system. Yeah? So you see here, for example, how these boxes are arranged. Each box has a name for the group, J4, Hickman, Sims, and so on. These are the sporadic simple groups. It also contains the order of the group. And if this group has another name, an alternative name, this is also written in the top. Yeah? Or then, that's the point here really, all these groups of Lie type. So each column corresponds to one type of groups of Lie type. So you have a Dynkin diagram, and then there's a number which stands for a finite field. And again, in the columns, they are arranged according to increasing order. And the last column is really the generic thing where you put any prime power for the size of the finite field you take. So here it's once more in all its glory. And as I said before, it shows very nicely that in order to study finite simple groups, you have to look at this huge area in the middle, which are the simple groups of Lie type. Okay, so let's now look at this class of groups. Now, it has become clear, I guess this was primarily through the work of Steinberg in the 1950s, 60s, that the correct framework for dealing with these things is really the underlying theory of linear algebraic groups. So this is now the tricky bit in this talk. So we have to assume some prior knowledge. So what we assume that you know, that you are roughly familiar with the basics about affine algebraic varieties. And here for these purposes, at least for the purposes of these talks here, I mean, you don't need to know that that these are reduced schemes or whatever. I mean, you can really take the naive point of view. You have the first object in this setup is k to the n. K is a field, k to the n. You take the space of n tuples of your field, and you impose a topology on this, the Zariski topology. A subset of vectors is called closed if it is the set of common zeros of a collection of polynomials. Yeah? In this way you define a topology, and this is the Zariski topology. You have a notion of morphisms. These are maps given by polynomials. Yeah? Essentially, this is really enough to get going here. You have to think about everything as being given or defined in terms of polynomials. Yeah? There's also a good notion of dimension for these affine varieties. K to the n has, of course, dimension n, and has some further natural properties. But this, this is somehow the background we need. And then we look at algebraic groups. So these are affine varieties which also have a group structure such that the group operations are morphisms of varieties, are given by polynomials. So of course the first example that you imagine here are matrix groups, groups of matrices. The matrix multiplication is of course given by polynomials in the entries of the given matrices, so these are easily seen to be algebraic groups in this sense. Huh? And this is actually what is written there, or equivalently, this is usually the first little theorem you prove, that these two conditions are equivalent. I mean, either you say I have an abstract affine variety together with a group structure. This is the formal definition of affine algebraic group, but this is equivalent to saying that you take that you consider closed subgroups of GLN. Yeah? Every abstract affine algebraic group can always be embedded as a closed subgroup into some GLN, and so they all arise in this way. So it's in the end, it's a very hands-on subject. You don't need, at least at these initial stages, the more formal, wider apparatus of algebraic geometry. And then, just as a first indication, I will explain this in more detail as we go along. How do you get finite groups from this setting? So first of all, you need to work not just over any algebraically closed field, but over an algebraic closure of a field with p elements. Yeah, that's the first thing. And the second, then, typically you get then your finite groups by taking fixed points of such an algebraic group under certain maps, which are Steinberg or Frobenius maps. So this I will explain later. It's just to see how you come from the world of algebraic groups, which are in the first place infinite groups, to the world of finite groups, yeah? By taking this idea of taking fixed points under suitable maps. And also a little word here. Usually, if you learn algebraic geometry, yeah, it looks like things are easier if you work in characteristic 0, or typically over the complex numbers, and somehow working with affine varieties over a field of prime characteristics is, yeah, there are some extra phenomena which make the whole thing technically a little bit more difficult, but we have to deal with this if we want to go to the finite groups. Huh? Okay, so that's the general frame. Yeah, and now the connection with the great theorem from the previous slide. So we look at simple algebraic groups, and so the definition for simple algebraic groups, it's a non-trivial group, and it doesn't have to be simple in the abstract sense, i.e. no normal subgroup at all. In this context of algebraic groups, you just require that there is no proper closed normal subgroup of strictly positive dimensions. So you may have some small zero-dimensional, that means finite normal subgroup. Yeah? And then if you start with such a group and do this procedure above, then this fixed point set has really at most one non-abelian composition factor, and all the finite simple groups in the great theorem arise in this way. And this here, at most, this is really a source of some little technical, well, it's not problems, but one has to take care of them. Yeah? For example, SLN over an algebraic closure of Fp is a simple algebraic group. It has a finite center, no other normal subgroups except those which are contained in this center, so it's simple. Now if you take these fixed points, so this I will explain, as I said, in more detail later, but you get, for example, the finite special linear groups. They are not simple either, they still have their little center. If you quotient out by the center, i.e. the scalars, you get in general a finite simple group, except if the values of n and q are very small. Yeah? So this is typically what happens there. Yeah? If as soon as your field is big enough, things are smoother. If the field is very small or the characteristic is very small, there may be special things that happen. But these special things that happen in these cases are not really the subject of my lectures here. I just want to mention that there are such things where one has to be careful. Yeah? Okay, so this is the general frame. Are we all right with this? Yeah? Okay. So having made a long speech about the importance of simple groups, we go away from this a little bit and look at a slightly larger class of groups, and these are the so-called connected reductive algebraic groups. And we will see in a minute why it is useful to enlarge the class of groups that we look at. So first of all, a few definitions. So let's just take any algebraic group over any algebraically closed field. First of all, this notion of connectedness is of course a purely topological notion. A topological space is connected. You can't write it as a disjoint union of two open subsets. There's also this notion of irreducibility, which means you can't write it as a union of two proper closed subsets, and in this algebraic geometry context, this translates into the condition that the algebra of polynomial functions on G is an integral domain. So this is this notion of connectedness which is essential here. Yeah? So in general, if your group is not connected, then you can always, there's a unique connected component which contains the identity element, and one of the first little theorems you prove this connected component, which a priori is just an open subset, it's actually a closed connected normal subgroup of finite index in your G. Yeah? So this is also one point. I mean, many things have a quite simple group theoretical characterization here. Yeah? So if you have an algebraic group which has no subgroups of finite index, then it's connected. Yeah? In particular, the finite algebraic groups are never connected. And again, yeah, the theory, the general theory that we develop will be about connected groups, but we will have to deal also with non-connected groups, because this will naturally show up. For example, if we look at centralizers of elements, these are typically closed, not typically, they are always closed subgroups, but in general they will not be connected. Yeah? And also this shows, or this indicates why it may be useful not just to develop a theory for simple algebraic groups, because such a centralizer may not be a simple algebraic group anymore. You need to find the correct frame in which you develop your whole theory, and as it has turned out, the correct general framework is this connected reductive business. Yeah, essentially every article in this area starts let G be connected reductive. So this one has to get used to that. Yeah. So this was connectedness. Now, what is this reductive? For this, we need another basic result about algebraic groups, namely this Jordan decomposition. Every element in your algebraic group has such a unique factorization as a product of two elements, of commuting elements, where one factor is semi-simple. That means it's diagonalizable under every closed embedding of your group by matrices, and the other one is unipotent, which means it's unipotent. Yeah? All eigenvalues are 1. Yeah, this is in GLN. This is easy. Well, it's a part of might be a part of an advanced linear algebra course to prove this, and the same thing happens in general for every algebraic group. And now the proof of this is not completely trivial. This one can see because the definition of this semi-simple and unipotent involves speaking about these closed embeddings. But we are lucky in our case. That will be interesting for us when we look at an algebraic closure of a finite field. Then the semi-simple and unipotent has a very nice simple characterization. Semi-simple elements are those which have order prime to p, and unipotent elements are just those whose order is a power of p. Just note, every element has finite order. Is this clear? Why does every element have finite order? Because if you have an algebraic group, you can embed it into a GLN FP bar, and here every element, every matrix that you take has only finitely many entries, and since I'm really just taking an algebraic closure of Fp and not just any algebraically closed field of characteristic P, every matrix will have entries in some huge finite field, so it will have finite order. So this is a first little observation. Yeah? Every has finite order. So this is one occasion where working in characteristic P is actually much easier than in characteristic 0, because the definition of semi-simple and unipotent is already there from abstract group theory. Okay, so now what is this reductive business now? Assume we have a connected algebraic group, then we need to define the unipotent radical, and this is also a typical thing in this whole theory. There are many definitions of certain subgroups which come with several adjectives like this, close connected, blah blah, and so on. Yeah? So this radical is the unique maximal closed connected normal subgroup just consisting of unipotent elements. Yeah? So in finite group theory, this would be, how is this called, OP of G or something, yeah? The largest P normal subgroup. You should think of it like this in the context of algebraic groups. Yeah? Of course, you have to show that this exists, it's unique and so on, but this is it. Yeah? And then you can always, so your group is called reductive if this is trivial. You don't have this ugly P normal subgroup in your group, and in general, by as it should be for a definition of a radical, if you quotient it out, it disappears. Yeah? So this factor is always then reductive. Okay, so what are some basic structure results about these groups? Assume we have such a thing. Yeah? Then first of all, the center, and this little circle there means connected component of the identity, the center may not be connected, is a torus. And what is a torus? A torus is an algebraic group which is just a direct product of copies of the multiplicative group. And then you may define a group to be semi-simple if this connected center is trivial, or it just has a finite center. Think of SLN. This is semi-simple. GLN is reductive. And in general, you always have this factorization. So your group is central torus times the commutator subgroup, where this commutator subgroup is itself then semi-simple. The intersection of the two is finite. And then you can go one step further. This semi-simple derived subgroup itself then is a product, a finite product of simple algebraic groups which commute pairwise. So it's not a direct product. They may intersect in some central elements, but they commute pairwise. So like this, one can at least say that although, as far as classification of finite groups and so on is concerned, we would just have needed simple algebraic groups. We have enlarged this class a little bit, but you see it's not too bad. A connected reductive algebraic group is a product of a central something plus finitely many simple algebraic groups. So there is not some enormously difficult extension problem between the simple groups involved like this, as you would have for a general finite group. Here, this is a fairly, I mean, there are some tricky things that can happen, how these centers and so on really intersect, but it's not too bad. This is manageable. Okay, so this is the general structure of these groups. Now let's look at some important subgroups which will also come up in every study really of these things. The first we mentioned already are tori. So a torus is just a closed subgroup which is itself isomorphic to a direct product of copies of the multiplicative group. So in GLN, of course, you have, for example, T. If you take diagonal matrices, this is a torus in GLN. In particular, it consists of semi-simple elements. It's an abelian group consisting of semi-simple elements. A basic structure theorem says that the maximal tori, in the set theoretic sense, are all conjugate in G. They all have a dimension, so this is a number you can attach to your group, and this is called the rank of G. Yeah? So it's the dimension of a maximal torus. By the way, I assumed now connected reductive. This theorem would also be true just assuming connected, but I didn't want now to have at every statement exactly what are the requirements. So that's the first important class of subgroups. The second one are the Borel subgroups. So these are again defined by such a sequence of adjectives: maximal closed connected subgroup. Yeah? Not normal, just closed connected subgroup. Here in GLN, this would be, for example, upper triangular matrices or lower triangular matrices would be a Borel subgroup. Again, all of these are conjugate in G. And an important notion here is also this flag variety. So you just look at the set of all Borel subgroups, and you can give this the structure of a projective variety, actually. I will not need this later. Maybe the others will need it at some point. I just wanted to mention this here. This is a very important object when studying the theory of these algebraic groups. Yeah? Okay. Now, a further important thing is, let's now take a maximal torus. As we said, they are all conjugate, so let's fix one. As I said, a maximal torus, in particular, it's connected, closed, and abelian, so solvable. So it will be contained in a Borel subgroup. No, this is what I want to say after this. Okay, so first of all, So where's the tricky bit here? It's abelian. Oh, okay, so T is of course contained in its centralizer, but if you have a reductive group, then you really have equality here. This is really where you need reductive. Yeah? This is one essential property of reductive versus general connected group, that the centralizer of a maximal torus is just this torus. And then the quotient of the normalizer by T is a finite group. Yeah? So in general, you would have normalizer modulo centralizer is always a finite group, but here then you have normalizer modulo the torus is a finite group. And this is called the Weil group of the torus. And now I can say the phrase that I said before. Since T is connected, abelian, hence solvable, it's contained in a Borel subgroup. So I choose a Borel subgroup containing T. Then the normalizer of this T and B form what is called an abstract Bn pair in the sense of Jacques Tits. So there's an abstract theory of these Bn pairs. You just take any group, two subgroups, B and N, and then there are 3, 4 axioms which these things have to satisfy to be a Bn pair. Yeah? And these Bn pairs arise naturally from connected reductive groups in this way. You take a maximal torus, a Borel containing it, and the normalizer of this torus, they form a Bn pair. Sorry?
He says if it's groups or algebraic groups.
Oh, yes.
In general, the notion of Bn pair is for algebraic groups?
No, it's for abstract groups, whatever. Just let G be a group. Two subgroups B and N are called a Bn pair and then there are 3, 4 axioms. Yeah? But of course the motivation of Tits to introduce this was of course the theory of algebraic groups, but you can do it abstractly. Yeah? And it also is extremely useful for studying the finite groups that we will look at. So why is one excited if one has a Bn pair? Well, we have this W, this Weil group. So just this little piece of notation. So W is this quotient of the normalizer by T. So every element, little w, has a representative in this N, which we just call by W dot. Sorry, the? No. For the abstract definition, you just need the N, and then the T would be B intersect N. Yeah, you would get it from there. But like when we build it, it's yeah okay. Okay, so there are two fundamental things which would hold for an abstract Bn pair. If you have these axioms, then this W is a Coxeter group. Huh? And you can even specify the generating set. These are all elements such that this union of these two double cosets is a subgroup of G. Yeah? This singles out certain elements of W, and then you have a Coxeter system here. And famously, you have this Bruja decomposition. So if you decompose your G into double cosets with respect to B, there are only finitely many of them, and they are naturally indexed by the elements of W. So this is what would come out of the general theory, but in these algebraic groups, yeah, you can see it also more directly. Okay, so as I mentioned already, the standard example to keep in mind is GLN. You take for T diagonal matrices, B upper triangular matrices, then the N, if you take the normalizer of this T here, these are just all monomial matrices. So all matrices which have exactly one non-zero entry in each row and each column. And if you quotient out the diagonal matrices, you just end up with permutation matrices. So the Weil group of GLN is the symmetric group Sn. Now let's look a little bit more into the internal structure of these subgroups. So B, remember, was in particular a connected, solvable subgroup. If we were in the world of finite groups, then I wouldn't be able to say much more. It's a solvable groups. It's a solvable group, may have a complicated structure, but here in this world of algebraic groups, these solvable groups have a very simple, clear structure, namely, you take the unipotent radical of B. So what was the unique, largest, close, connected, normal subgroup consisting only of unipotent elements, so this OP thing. This is a normal subgroup, this U. You choose any maximal torus actually in B, and then of course the intersection is trivial, and your group is just the semi-direct product of these two. So it's a very simple, you have a large P normal subgroup, and a complement which is a abelian consisting of semi-simple elements. Yeah? And just as a little side remark, so this little sign there means semi-direct product. You could just read it in the sense of abstract group theory, normal subgroup, complement, intersection, and product, and so on. But if you speak about algebraic groups, there's a little subtlety. You also have to require or something else, something additional is true, namely that this product map is actually an isomorphism of varieties. Yeah? This is one of the things that I will not go into too much details, but if in general you see an abstract semi-direct product of algebraic groups, then you always have to be a little bit careful. Yeah? There are these things like you take, for example, G. You take GL2 over an algebraic closure of the field with two elements. You have in there a normal subgroup, namely SL2. And then you have the scalar matrices, Z, just and then G is abstractly the semi-direct product of these two, but it's not a semi-direct product in the sense of algebraic groups. This product map is not an isomorphism here. Yeah? It's always, so G is N. No. Well, they are both, okay. Sorry?
Abstractly, is it?
Yes. But abstractly, it's even a semi-direct product or direct product, but not in the sense of algebraic. You have the product map, but it's bijective, but not an isomorphism. Yeah? So, as I said, this is not the purpose of these lectures is not to dwell on these strange things that may happen in characteristic P, but one should just be aware of it. Yeah? Sometimes you have to be careful there. This could not happen in characteristic 0, but it can happen in characteristic P. Okay, so that's in. Yes. Here it's really always a true semi-direct product in the sense of algebraic groups. So, having seen these Borel subgroups, with this semi-direct product decomposition, there's a slightly larger class of subgroups which are also very useful to know in various contexts, and these are the parabolic subgroups. So the algebraic group definition of a parabolic subgroup is you have a closed subgroup such that the quotient variety is actually a projective variety. But in more concrete elementary terms, this just means that your P contains a Borel subgroup. So in particular, Borel subgroups are parabolic. G mod B is a projective variety. Yeah? And these parabolic subgroups, this is why it's a generalization of the Borel setting, they also have this nice semi-direct product decomposition. You look again at their unipotent radical, and then you have a complement, which now, of course, is not just a torus, but it's what is called a Levy complement, and this is again a connected reductive algebraic group. Yeah? If you start with your G in the beginning, connected reductive, then these parabolics also have as L as complements connected reductive groups. So this provides in particular a useful family for doing inductive arguments with algebraic groups. Yeah? Yeah? Namely, you look at this class of subgroups, Levy complements in some parabolic subgroups. So again, if you want to see this in GLN a typical parabolic are subgroups which are not just upper triangular, but which are block upper triangular. Yeah, so it's, in this case, it's really a true generalization of this Borel thing. And the Levy complement is just the direct product of these diagonal blocks here. Okay. These Levy subgroups also have a let's say a more intrinsic definition. You don't need the surrounding parabolic subgroup to see them. Namely, they just come up as centralizers of tori. Yeah? If you take a maximal torus, remember, the centralizer is just the maximal torus itself. If you take a torus which is not just the maximal one, of course the centralizer will be bigger, but what you get is at least such a Levy subgroup, and all Levy subgroups arise in this way. This is also a useful characterization of these subgroups. And finally, parabolic subgroups can be seen also in this setting of Bn pairs. Remember, we have our G, the B and the N, and then we can get a complete overview over all parabolic subgroups which contain or given B they are in bijection with subsets of the generating set of my Coxeter group just by taking B together with these generators. Yeah? So you get if your W is a Coxeter group of rank n, if S has n elements, then you have 2 to the n parabolic subgroups containing a given B. So it's a nice combinatorial picture here. Okay, so this is the structure about the structure of connected reductive groups and some important subgroups in general. And from now on in my talk, let's now try to go towards the finite groups of Lie type. So we work over an algebraic closure of the field with P elements. Well, first of all, this field is not too difficult to imagine. For every power of P, you have a unique subfield with Q elements, and K is just the union of all these finite subfields. And then you do the following. So as I mentioned already in the beginning, we want to get finite groups by taking fixed points of algebraic groups under certain maps. So the simplest incarnation of such a map is here in GLN. So you have your group GLN over this field, then you can define this map. Just take a matrix and raise every matrix entry to power Q. This is a homomorphism of groups. It's also an algebraic map, because the coordinates of the image are given as polynomials, just a monomial in the coordinates of the original matrix. It's actually a bijective homomorphism of algebraic groups. And if you take the fixed points, then you see these are all matrices which have the property that Aij power q is Aij, which means that Aij is an entry of the finite field Fq. So you just get your finite group GLN-Q in this way. Yeah? This is the, I mean, there's a formal, general, abstract definition of Frobenius maps, but this is the essence of this procedure. Yeah? You have your matrices, raise matrix coefficients to power q, take fixed points, you get a finite group. This is the idea. Yeah? So, how do you make a general definition out of this? Well, so we take any linear algebraic group over K, assume we have a map from G to G, then I call this a Frobenius map if, well, we saw that every algebraic group can always be embedded as a closed subgroup into GLN. So the definition is if I can find an embedding such that my map is just given by this FQ. Yeah? So it's a very, in the end, a simple definition. Yeah, so you have your G, here's the F, you embed, here's GLN. Here you have this map FQ, and you just want that this commutes here. Yeah? And then you can, then this F will also be a bijective homomorphism of algebraic groups, and the fixed points are a finite group. So this then, the general definition, a finite group of Lie type is a group of this form, where G is our favorites, the connected reductive ones, over this field K, and F is slightly more general, not just a Frobenius map, but I'm just requiring that some power of F is a Frobenius map. Yeah? Just a slightly more general setup so that we can really include all the simple, finite simple groups of Lie type which show up in the big theorem. Yeah? Namely these, so if you are familiar with these, there are these Rie groups and Suzuki groups, and for these you would really need here some proper power of F. Yeah? You can't just define them using a Frobenius map. But again, I will not consider this any further in my talks here, because if you do everything in this more general setting, it gives rise to a few but it's really technical complications every now and then, and I don't want to go into these. Yeah? So we could just take Frobenius maps throughout, but this is the general definition.
There's a finite number of cases where you need this?
When you take simple groups, yes. It's exactly these three. Yeah. Okay, so you need now some technical device to transfer results about the algebraic groups to the world of the finite groups. Yeah? After all, in the end, if we want to study the finite groups, it first looks like we make our life much more complicated by going to this bigger world. So we need some tool to go back and forth between these two. And this tool is the Lenk-Steinberg theorem, which just says the following. Yes? Just when this power m is really bigger. Yeah? So of course I consider unitary groups or such things, but not these.
So they will not be a
Frobenius. You get the unitary groups also by a Frobenius map, because it probably doesn't work with the definition of the unitary groups that you have in mind by taking n by n matrices and taking some strange automorphism. You would have to take another embedding into a bigger GLN, and then you can really get it as with a Frobenius map. Huh? You would have to take 2n by 2n matrices, and then so in the formal sense of Frobenius maps, unitary groups are just fine. Huh? There's nothing twisted about them. Yeah? But these Suzuki and Ree ones, they are really twisted. Yeah? Okay. So, Length-Steinberg. We take a connected algebraic group. Doesn't have to be reductive, just connected. And we take such a Steinberg map. Yeah? Bauer is a Frobenius map. Then this thing here, this map, G goes to G inverse f of G is surjective. Huh? It looks like a simple innocent statement. The proofs that are available now are also not so terribly difficult. But this is really the thing that you use all the time to prove things about finite groups of Lie type. Huh? So let's just take one example. It's okay. Yeah? So one example, remember we take connected reductive, Steinberg map, we have a Bn pair. I said in general, such a connected reductive group has a Bn pair. You take a maximal torus, take its normalizer, take a Borel which contains the maximal torus. If I just start like this, there's no guarantee that this B and N are invariant under this F. Yeah, claim, we can assume, we can choose the ingredients of the Bn pair such that they are also invariant under this F, and then I can take also fixed points under that. So let's go once more, let's just go once through such a proof that you see the beauty of this Steinberg theorem. So we start with any B, any Borel, and I want to modify it to get an F-stable one. Well, first I apply F to it, because F is a bijective homomorphism of algebraic groups. There's also some little theorems about algebraic groups that you have to know. Yeah? So the image will, of course, be, again, a solvable subgroup, but will also be connected and closed and so on. So it's, again, a Borel subgroup. I said that all Borel subgroups are conjugate, so this F of B will be conjugate to B by some element G in G. And now, once you have seen this 2-3 times, there's the reflex. I have a little g, so I use Length-Steinberg to write it as x inverse f of x. And then we look at this, and you see, of course, one has to prepare these talks. Yeah? There are a power of 2 mistakes that you can make. Yeah? If you wrote there GB G inverse, or here now x inverse bx, yeah, and a power of 2 mistakes you can make. Yeah? Okay, so I hope this is correct. Yeah? So let's apply f to this. So it's of course f of x, f of b, f of x inverse. F of b is the g inverse bg. F of x is xg. So we write this, and you see the little g's cancel out. And I just end up with xb x inverse. Huh? So my xb x inverse is f stable. We started with b, we replace it by this conjugate, so we have found an f stable Borel. And then we just do the same argument inside the b. My t is inside b, it may not be f stable, but all maximal tori are conjugate, so I can just do the same game. I get an f-stable b, t inside b, and then of course the normalizer of an f-stable something will be f-stable. Yeah? Once we have this, you see then f induces, so if t is invariant under this automorphism, n is invariant under this automorphism, then f induces an automorphism of the quotient. So just an automorphism of this finite group W. And then also a little theorem here. If you take the fixed points of B, the fixed points of N, then they form such an abstract Bn pair in the finite group. With Weil group, the fixed points under this gamma. Yeah? So a little consequence also, the fixed points of a Coxeter group under such an automorphism is again a Coxeter group. So this is how really you go from the algebraic groups to the finite groups, and everything works nicely together with these also in this Bn pair setting. So let's just come to the last slide here, example. GLN. Our standard Bn pair in GLN, upper triangular matrices, diagonal matrices, W is the symmetric group. So here we get two families. Of course, this is now, this is not the right way to make the point to you, but anyway. So we get two families of finite groups from here, namely as follows. First we take, as our Frobenius here, the nice guy, just raising matrix entries to the qth power. Of course, here we don't have to do anything. My B will be F stable. If I take an upper triangular matrix, this property will not change. If I take a diagonal matrix, this property will not change. And if I take a permutation matrix, this FQ doesn't do anything to it. Huh? So here I really have the fixed points of the whole thing is GLN, B and T are F stable, gamma, the induced automorphism on W is the identity, so my W gamma is also W. Yeah? But I have a second possibility. So I define F prime, so I first do FQ of G, raise matrix entries to the qth power. Then I take transpose inverse, and I conjugate by a permutation matrix, which is this N0, so it's the worst or longest permutation. Yeah, you just send one to N, I mean, it's this matrix, yeah? So this N0 is this permutation matrix. Yeah, why do I have to do this? So first of all, we see F prime is a morphism such that its power is the FQ squared. If I do this twice, the transpose inverse goes away. This N0 has order 2. It goes away, so I've just raised every matrix entry to the power Q squared. So just FQ squared. So in this sense, it's a Steinberg map, but as I said, you can also, anyway. Yeah? So this is the unitary group, and the reason why I did this conjugation with N0 is that then my B is still F prime stable. You see this? If I take an upper triangular matrix, I raise matrix entries to the qth power, still upper triangular, transpose, lower triangular, inverse, lower triangular. But if I then conjugate by this, I get again an upper triangular. This is the only reason for doing this extra conjugation, that my B just remains F stable here, F prime stable. The T anyway is fine, but now you also see the gamma prime on permutation matrices. This is just conjugation by this thing. Yeah? And then you see the fixed points of this is not Sn anymore. The fixed points of Sn under this map given by conjugation with this permutation is a Weil group of type Bm or Cm, depending on whether n is even or odd. Yeah? So the unitary group has a Bn pair where the Weil group is a group of type B or C. Okay, so that's my first talk. Continuation tomorrow. Thank you. Yes?
You said that this unipotent radical, it's just a P group.
Yes.
P groups can be pretty bad.
Yes, this is why we quotient them out, yeah? To get reductive groups. Yeah.
Sure, that'd be
Yeah.
interesting.
Yeah, that's okay. But if I want to study simple groups, then they just annoy me. Yeah, so.
Okay, if there's no further question, then we have a coffee break.
Okay.